Okay, now we are in the last part of this electrostatics, and by this session we are going to complete this electrostatics. Hope you are good with this, all the concepts what you have learned in the electrostatics. And now we are in the last part of this, that is in the capacitors. We talked about the capacitors and we came to know how the energy stored, what is the energy stored in the capacitor, what is the capacitance of a capacitor, what is a parallel plate capacitor, and some of the expressions or formulas related to that. And now, grouping of the capacitors, that means a combination of capacitors or grouping. Here, when I talk about the combination or grouping, suppose if we are having more than a capacitor, 2 or 3 or 4, how we can group them? So here, already when you are talking about the resistances in your previous classes, there in your 10th class, you might have learned about the grouping of the resistances. There you just understood there how we can group the resistances. The grouping is done either in the series or in parallel. That's a basic combination, either series or parallel. And next, after that understanding that, we'll work a combination of both series and parallel. So first let us understand, here also the same thing is to be followed, that is grouping basically in the series and the other one is the parallel. So here in this, first let us talk about this series combination. Actually, why we have to go for these combinations? When you are talking about the resistances, when you are grouping the resistances, then you understood. When you are grouping the resistances in series, the effective resistance increased. That means to increase the effective resistance, you just combine the resistances in series. Similarly, when you want to decrease the resistance, suppose if you want to, a resistance is there, and if you want to decrease that resistance of that particular resistor, what you are going to do is you are going to take another resistor and make it in a parallel, bring it in the parallel combination. So in the parallel combination, their resistance has effectively reduced. So here, either to increase the resistance or to decrease the resistance, the effective resistance, we grouped either in the series or in the parallel. In the similar manner, in the capacitors also, the effective capacitance can be increased or it can be decreased by grouping them. So let us see what it is going to happen here in the case of the series combination of the capacitors and the parallel combination of the capacitors. First we will go with this series combination. Now here I'm going to take the 3 capacitors. First, what is the series combination? What is the series combination? Here we know that we have, if we just take the parallel plate capacitor, it is always indicated by two parallel lines, and one will be the positive plate, other one will be the negative plate, and for that we are going to connect this to the positive terminal, and either we can add this or we can connect it to the negative terminal, isn't it? So like this we are going to just combine them, connect it. So suppose we are having more than a capacitor. If you are having more than a capacitor, now grouping them, what you are going to do is the negative end of one capacitor is connected to the positive end of the other capacitor, and so on. That means, suppose if we are having capacitor whose capacitance is C1, another capacitor whose capacitance is C2, another capacitor whose capacitance is C3. So here, and if we just connect it to this, if we are applying any voltage or any source to it, this becomes positive and this will be the negative, and this negative is connected to the positive and the negative is connected to the positive, and so on. This type of combination we will be calling it as the series combination. So how to say it in terms of say it in a sentence? or using the words means here, the negative plate of one capacitor connected to the positive plate of the other capacitor, and so on. This continues. This combination we will be calling it as the series combination. So let us see what is the effectiveness of the capacitance of these capacitors when they are grouped in series. So now we want to find the effective capacitance. And here, because let us see here, the potential V is applied. Potential V is applied. And we know that here, if the potential V is applied here in this series combination, here we are going to see the potential difference as V1 between these two plates, V2 across these two plates, and V3 across these three plates. And if you look at the charge, if this is given as plus Q, this will be as minus Q. So if one is positive, other will be the negative with the same amount of charge. So here in this series combination, the charge remains same. This is a very important point. So in series combination, charge remains same. Charge remains same. So now if it is plus Q, this will be plus Q, and this also will be plus Q, and this will be minus Q, and so on. So now this is what we are going to observe initially during this combination. What do we observe here? If we are giving applying potential V, here we are going to see the potential as V1 and V2 and V3. And if we just add this V1 and V2 and V3, you are going to get the total potential applied there. So now this is the capacitance C1, this is the capacitor with capacitance C2, this is the capacitor with capacitance C3. Let us think that here, due to this combination, we are going to see an effective capacitance. Let us indicate that by means of a capacitor, its effective capacitance is C. Due to this combination, this is the capacitor. So now the charge is same, so this also will be having the same charge. And because we are applying potential V, for this capacitor, the potential is V. So from this we are going to extract the effective capacitance. So here we understood that here it is V is equal to V1 plus V2 plus V3. Coming to the capacitor C1 here, near this capacitor C1. So at C1, charge applied is Q, its potential is raised to V1, and the capacitance is C1. So V1 is equal to Q by C1. Similarly at C2. At C2 here the capacitance is C2, charge is Q, and potential is V2. So at C2, V2 is equal to Q by C2, and the same thing at C3, V3 is equal to Q by C3. And we just, because of these three, we are going to see the effective capacitance is C, and the charge is Q, and the potential is V. And near this capacitor here, V is equal to Q by C. So now we came to know V is equal to V1 plus V2 plus V3. V is equal to Q by C. V1 is equal to, it is Q by C1, and V2 is Q by C2, and V3 is Q by C3. And taking Q common on both sides, they get cancelled. So we are going to get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and this is your effective capacitance. So the effective capacitance is 1 by C1. It is not the effective capacitance. Just keep in mind, it is not the effective capacitance. It is the reciprocal of effective capacitance. It is the reciprocal of effective capacitance. The reciprocal of effective capacitance is the sum of, these are the individual capacitance, not the individual capacitance, actually they are the reciprocals of individual capacitance, sum of the reciprocals of individual capacitance. So how can we tell a sentence here? The reciprocal of effective capacitance is the sum of the reciprocals of the individual capacitance. So from this we can understand one thing here. Its capacitance is C1, its capacitance is C2, its capacitance is C3. Okay. So now C1, C2, C3 is there. And let us think in this, among the C1, C2, C3, this is having the least capacitance. This is least among these three. So I can show it like this. C1 is less than C2 less than C. Sorry, this is least, no. So it is C1 is greater than C2 is greater than C3. That means C3 is least among all these three. We just observe this effective capacitance, CE. This effective capacitance will be less than the least. So effective capacitance is less than the least. So from this you might have understood one more statement here, one more important thing here. If you want to get the, or if you want to reduce the capacitance, then how can we make a combination of capacitors? Means we are going to connect them in series. If you want to get the least capacitance, or if you want to reduce the capacitance, we can combine, we have to combine the capacitors in series. So the effectiveness gets reduced when they are combined in the series combination. And in this, making this derivation, the only thing what you have to keep in mind is this is the first one, that is in series combination the charge remains same and V is equal to V1 plus V2 plus V3, because here the applied potential is V, and at these capacitors we are going to observe as the different potentials here, and if we add these potentials we are going to see this applied potential. So basing on these two things only we have derived this expression, and this is to be noted down. Okay, now pause the video, take the screenshot, and coming to this next combination, that is parallel combination. After understanding the series combination, you can understand easily this parallel combination. And already in your 10th class you learned about this resistances combination, so this can be easily understood. Okay, right. Now, when the combination is said to be the parallel combination, suppose if you are having capacitors C1, C2 and C3. Okay, told you the capacitors are connected by two parallel lines. Okay, and one is connected to the positive terminal and the one is connected to the negative terminal, or else it can be connected to the earth. Now, if this is to be connected to what you call it as the potential applied here, potential difference applied, then is source. So now what we are going to do is this becomes the positive end, and this becomes the positive end, and this becomes the positive end. So all the positive ends connected to a point, and all the negative plates connected to the another point. So such type of grouping we will be calling it as all the positives connected to a point, and all the negatives connected to negative plates connected to the another point. We will be calling this combination as the parallel combination. And I'm going to connect it to a source which provides the potential difference V. So if it is providing potential difference V at point A and at point B, the potential will be as V. And because all the capacitors are connected to the same points, their potentials also remain same. So this is V, for this it will be V, and for this it will be V. Okay, again I am repeating here. Now we are connected to the source which maintains the potential difference V, and because it is connected to the points A and B, at A and B or across A and B, the potential difference will be V, and as these capacitors are connected to A and B individually, then their potentials also will remain as V itself. So at capacitors C1, C2 and C3, the potential difference is V. That means in parallel combination, V remain same. Okay, the V remain same. And here, as these are connected in the parallel, the current automatically will varies. So as the current varies, the Q also will change. The Q will not be same for all these. It depends upon the capacitors. So here it is let it be Q1 and Q2 and Q3. So here in parallel combination, Q is, so here in parallel combination, we understood at C1 it is Q1, at C2 it is Q2, and C3 it is Q3. I should not say here the Q is divided into Q1, Q2, Q3 because initially we are not having any Q here. So from this we are going to get the total charge or net charge, the total or net charge as Q is equal to Q1, Q2 and Q3. Okay. Here in this combination, because the capacitances are different, so the charges also will be different, Q1, Q2 and Q3. So if we add these, we are going to get the net charge as Q is equal to Q1, Q2 and Q3. So for this capacitor, it is C1 is Q1, capacitance is C1, charge is Q1 and V. For this capacitor C2 and charge is Q2 and V. For this capacitance C3, Q3, V. Okay. Let this combination form a capacitor whose capacitance is C with the total charge Q, potential difference applied is V. Okay. So that means here, due to this combination, we are going to get effective capacitance. So now just I am assuming a capacitor with effective capacitance C, and the net charge on this will be equal to the sum of the charges. Q is Q, that is Q is equal to Q1 plus Q2 plus Q3, and the V remains same, so it is V. Okay. So now at capacitor C1, now what I am going to do is bring the relation in the form of Q is equal to CV. Because here I am having Q is equal to Q1, Q2, Q3, I am going to use this for deriving. So I am going to write it in the form of Q is equal to CV. At C1, Q1 is equal to C1V. Q1 is equal to C1V. At C2, the same thing. Q2 is equal to C2V. At C3, Q3 is equal to C3V. And for the effective capacitance, I have considered a capacitor whose effective capacitance C. So for this, Q is equal to CV. Now from this, Q is equal to Q1 plus Q2 plus Q3 and Q is equal to CV. It is Q1 is C1V, Q2 is C2V, Q3 is C3V. V is common here. So effective capacitance C is equal to C1 plus C2 plus C3, and this is your effective capacitor. So here effective capacitance C is equal to C1 plus C2 plus C3. That means sum of the individual capacitance. So effective capacitance in this parallel combination is C1 and C2 and C3. So from this we are going to extract one important point here. If you want to increase the capacitance by grouping, what method we follow here? We follow the parallel combination. By this grouping, we are going to increase the effective capacitance. Okay. So this is regarding the series combination and parallel combination. Take a screenshot and we'll come with the numericals. Okay, here a numerical, simple numerical is there. How to solve such type of problems here? If both the combinations are seen here, both these, we just observe these three, they are in series and these three are in parallel. So look at the problem once here. Three capacitors each of 0.003, some capacitance is there. That means all are having the same capacitance, are in series, and these are connected in series with some other which are in parallel. Calculate the total capacitance. So here the mixed combination is there. If you find such type of mixed combination, to avoid confusion, usually we just do like this. In this combination, just see where is the parallel combination. So here we are going to see the parallel combination here. So first solve the parallel combination. So when these are in parallel, we know the effective capacitance is C plus C plus C, that is 3C. That means now this due to these three, it results a capacitor whose capacitance is 3C, and you can imagine how it will be like. 1, 2 and 3. These three are like that only. And because of these three, we are going to get a 3C capacitor. Now if you just observe the picture here, all these are in series. If all these are in series, then the effective capacitance 1 by C is equal to 1 by C plus 1 by C plus 1 by C because of these three, and it is 1 by 3C. And it is 1 by C is equal to, take 1 by C common, 1 by 1 plus 1 by 1 plus 1 by 1 plus 1 by 3. So 1 by C is equal to 1 by C into, because of this 3 plus 3 plus 3 plus 1, it is 10 by 3C. So here it is 1 by C is equal to 10 by 3C. So C is equal to 3C by 10. So what is the capacitance here? It is 3C by 10. 3 into, what is the answer here? It is 0.003 micro 10 power minus 6 by 10 F. So it is 0.009 into 10 to the power of minus 7 farads, or so this will be your answer. Okay. So here the main thing, the important thing, just solving such a grouping combination is, in order to avoid confusion, the simplest thing is just focus from the beginning, from where the parallel combination is there. First solve the parallel combination and bring all the things into series, then it becomes easier. Then you can imagine a picture instead of making every time a diagram like this. Okay. So take a screenshot, pause the video and take the screenshot, and we'll go with another problem. Okay. Here another combination is given, a simple. If you just look at it as a complex, it looks as a complex. If you look at it as simple, it is just a simple one. So I told you, if you want to find the effective capacitance from this, let this be C1, C2, C3, C4, C5 and C6. So first, where will you start? Where there is the parallel combination. First I will start from here, C5 and C6. And from this, I will find out the effective combination. We can here an easy way. If you are having two capacitors, C1 and C2, if it is a series combination, what I will do is, what you will generally do, 1 by C is equal to 1 by C1 plus 1 by C2. So for going with instead of going with a very big calculation or something confusing calculation, simply go like this: C is equal to C1 C2 by C1 plus C2. If you are having two capacitances, C is equal to C1 C2 by C1 plus C2. What is the effective capacitance here? C is equal to C5 C6 by C5 plus C6. So no need to go for, if you just do like this, you are going to get the answer in the reciprocal form. Again you have to write it in the reverse form. So instead of going with all headache, just try to use this whenever you find true like this. And because of this, I am going to get an effective capacitance, like let it be some Cx. You know how it appears here? This is C1 and this is C2, and so now this will be as Cx. Okay, and this is your, now here C3 and C4. C3 and C4, they are in, sorry, these two are parallel. Come on. Parallel means what we are going to add. It is C5 plus C6. Parallel means we are going to add, we are going to C6. And here look at C3 and C4. C3 and C4 means it is equal to C3 into C4 by C3 plus C4, it is Cy. So now here it is your Cy. Okay. Now again here C2 and Cx are in series. Again in series combination, we are going to get, it is as C2 into Cx by C2 plus Cx, let it be some Cz. Okay, so here it will be like this. It is Cz and it is Cy. Now just look at this Cz and Cy, they are parallel. Parallel means we have to add them. So now because of Cz and Cy, like we are going to CQ. So it is CQ and this is C, and we got it as a parallel. So just whatever the calculation, maybe don't bother about the calculations, just understand the procedure. First start from a corner which are in parallel in combination, parallel at them, and because of that you are going to get one single capacitor. Now just solve this. We are going to get a single capacitor. Now just solve this. We are going to see that, and like this we are going to complete the problem. Okay. So likewise you can solve whatever the combination it is. Just you can take 2 or 3 examples and you can solve it. Okay. Right. Now going to one more very simple problem here. Find the effective capacitance between terminals A and B. C1 is equal to 1 microfarad, C2 is 2 microfarad, C3 is 3 microfarad. Okay. So in this, if you just look into the capacitors here, and if you look into this connection here, to look it may be very complex. What are these lines or the circuits are drawn like this? How to solve this problem? You cannot understand whether it is in series or whether it is in parallel, how to go with the problem. But if you just look with your mind properly, you can understand it very easily. Simply they are in a single combination. Just look at it properly here. You can understand if you just look into the mind, look with your mind, okay, with physics mind, you can simply say that it is in a single combination. Just look here, look at this capacitor. Suppose if it is a positive terminal, C1, it is connected to the A. That means this one plate is connected to A, and coming to C2 here, the C2, this end is connected to A. That means one end is connected to A. And C3 also here, this plate is connected to A. That means in C1, one plate is connected to A, C2, one plate is connected to A, C3, one plate is connected to A. That means all one plates connected to one point. And coming to the another one here, another plate here, the C1 of another plate connected to B, C2, another plate connected to B, C3, another plate connected to B. That means all other plates are connected to the another point. All one plates connected to one point, all another plates connected to the another point. What is the combination? Parallel combination. So all these are in parallel combination. So what will be your answer? C is equal to C1 plus C2 plus C3. Okay. So even though the problem looks complex, it is very simple if you look with your good mind. Okay. So now this is the problem and these are the numericals, and that's about this electrostatics chapter. Okay. See you in the next chapter. Take care. Bye.